Okay, I'm going to answer this question. Thank you very much, Waleed, for asking this question. Section 6, 4.5, practice question 11. Part A, no friction involved. And you've got an inclined plane here. And at the bottom of the inclined plane is a mass that's attached to some type of shooter with a spring in it. And we want to know by how much do we have to compress this spring, right? So that we shoot this out and it gets to a certain height, y final of 0.057 meters. So that's how high we want it to get. How much do I have to compress the spring by to get it to that height? No friction. Well, like many of these questions, it lends itself to being solved by using the law of conservation of energy. So the total energy initial is equal to the total energy final. Now, the initial energy is all elastic potential energy. It is all the energy stored in the spring. The object has no height. Y is 0, no gravitational potential energy. The object is not moving, no kinetic energy. So that's why it's only elastic potential energy. Then it's shot. So boom, it goes up, 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 gets to here and stops. It's not attached to a spring anymore, so there's no elastic potential energy here. It's not moving, so there's no kinetic energy, but it has gained height. It now has height in the gravitational field of the Earth. Therefore, it has gravitational potential energy. That means all of that elastic potential energy has turned into gravitational potential energy. So I write out the expressions here. All right. All I need is the magnitude portion of the new height. So that's why I just have YF there. I do some rearranging here. I multiply each side by 2. 2 times a half is gone. I divide each side by K. There we have it. So now I have an expression that will tell me by how much I have to compress the spring by. 2 times the mass, which is known. We know we're on planet Earth. We know how high we want it to get. And they gave us the spring constant of the spring. You would calculate this. Of course, you'd have to square root, and then you would have your solution. Now, in the second part of this question, there is friction. So we are very interested in the path length, and we're going to define the path length as delta D right here. It moves through this distance. And as it's moving through this distance, it's experiencing a force of friction down the ramp. It's trying to oppose the motion. Having said that, the way to attack this problem is still through the law of conservation of energy. And what it says here is that at the beginning, all the energy is the same as it was when there was no friction. All the energy is elastic potential energy. But now that energy total that you had initially is converted into gravitational potential energy final, because we still want it to get to this height, right? But some of that energy was lost through friction, through thermal energy being transferred as heat. So all of that initial energy goes to getting it to the new height and energy lost through friction. So let's put in the expressions for each of them. This is the same as part A. This is the same as part B. And here is the expression that I showed you a while ago for work thermal. Force of kinetic friction, magnitude, displacement, the magnitude. So we still want to solve for how much do I have to compress the spring by. So I still multiply each term by 2, multiply by 2, half cancels out, multiply by 2, and multiply by 2. And I still have to divide each term by k, the spring constant. Divide by k, divide by k, divide by k. So now let's take a look at this. Let's compare this expression without friction to this expression with friction. The first term here is exactly the same as the original term there without friction. So if you want to find out how much you have to compress the spring by, with no friction, it's just this term. With friction, you still have that term plus more. So if you want to get it to the same height as this occurred without friction, you're going to have to compress it more. These are going to add up. This original term plus that will give you a larger x squared and therefore a larger x, meaning you have to compress the spring more if you want it to get to the same height where there was no friction. Okay, I hope that helps.